Okay, so we're going to start off looking at conservation of energy by recapping some stuff that we have met previously, or we should have met previously. So first thing I'd like you to do is just pause this video and in your booklets, have a go out answering these questions, see if what we can remember. Okay, so if you need more time, just pause the video, but we're going to crack on. So first of all, what is work done? So work done is the change in energy of a system or object. So if we increase the energy of an object, we've done work on it. And if the energy of an object decreases, it's done work on us or its surroundings, essentially. But that's the key idea. Work done is the change in energy. So energy or work are measured in joules, obviously named after a famous physicist, did lots of work in engineering and thermodynamics and stuff. How is work done calculated? So to be specific here, we're talking about mechanical work done, if we're being pedantic about it. It's done by calculating the force times the distance the object has moved in the direction of the force. So that's often shortened to W equals FD. And change in GPE, again, we met last year, it's calculated using this equation. So change in GPE is mass times gravitational field strength times change in height, often simplified to this equation, delta GP equals mg delta h. The reason there's all of these changes in here, or the deltas, is because we at no point are calculating how much GP an object actually has, but we can calculate how much it gains or loses by its height change. Okay, so that's the stuff that we've met before. So you may have met before, but I want to emphasize, because it kind of links those two concepts, is where the equation for change in GP actually comes from. So essentially, change in GP is defined as the work done to change the height of an object. So if we think about an object, let's say we are letting an object fall, like we're doing here. So it starts up here, and then the weight force of the object is doing work to make it fall, so it's going to accelerate essentially. So remember that work is force times distance. And then the force in this case is going to be the weight force of the object. So this is why I'm not using W's, otherwise we'd get confused. So the force in this case is the weight, which is the mass times gravitational field strength. The distance is the change in height, because that's the distance in the direction of the force. So we can see that the work done would be mg delta h. And since change in GPE is defined as the work done to change the height of an object, we get that GPE equals mg delta h. So that's where the equation actually comes from. It's actually just a unique expression of work done. So work done in a particular scenario. So this equation calculates the work done by a weight force. So when we're doing conservation of energy expressions, we're never going to be thinking about the weight force doing work anymore. We're just going to use GP to account for that. Okay, so let's something new. So the new kind of energy we're going to look at calculating is kinetic energy. So let's add this to the equation section of your booklets. So kinetic energy is calculated by doing half times mass times speed squared. So kinetic energy is a type of energy, so it's going to be measured in joules. The half is unitless or dimensionless. Mass needs to be in kilograms, and the speed needs to be in meters per second if we want to calculate and make predictions correctly. Okay, so that's our equation. So let's look at how we're actually using conservation of energy to give us some. So before we do that, actually, there's one thing I'd like to address is that looking at where this kinetic energy equation comes from. Now, I'll stress straight away, this is not part of the course, but it is interesting to see where your equations come from, so I'm going to show you anyway. So here we go. So kinetic energy is defined as the work done to increase the speed of an object from stationary. Okay. So we're going to be using our work done equation because we see kinetic energy is work done. So work done is force times distance. If we're increasing the speed of the object, we are accelerating. So we can use this expression for the resultant force on the object, F equals ma. So therefore, we can get an expression work equals MAD. Like this. So work is mad. Anyway, so we can now start making some substitutions. So acceleration, we know, is change in velocity over time taken. change in velocity we can express as final velocity minus the initial velocity, which we can simplify to this because we're told it's initially stationary. So that's what we're using here. So because the object is stationary, that means u, or the initial velocity, is 0. We can do the same thing for distance. So we know that average speed is distance over time. So that's going to mean that also that average speed is the final plus the initial divided by 2, because that's just us calculating the average. Equating those two things together, we get this expression here, where again we've removed u because u is 0. So we've got distance is speed times time divided by 2. So this v here is final speed of the object, incidentally. If we put those three things together, what we get is work done is calculated like this. We can cancel out the t's, and we can simplify it to this, that work done is half mv squared. Kinetic energy is the work done to increase the speed, so that means kinetic energy is half mv squared. So this is where this equation actually comes from, and we go about testing it experimentally if we want to, which we might do in a future class. Okay, so that's our kinetic energy. Okay, so why is it useful to calculate kinetic energy and work done, etc.? So it's all very nice having these equations, but what is the point of them? Well, the reason it's useful is because there is a universal law of physics that utilizes them. So it's the law of conservation of energy. So energy cannot be created or destroyed, only transferred into a different form. So the reason it says universal is because it applies to the whole universe. So everything in the universe has to obey this law of conservation of energy. So that's why it's so powerful. So we can't create or destroy energy, we can only change it into a different form. Okay, so if we can identify scenarios where no work is done on a system, so some examples would be if there's no friction acting, if there's no drag acting, no one's coming along and pushing it, things like that. Now, the reason it's useful is because we know the total energy of that object must stay the same because no work has been done on it. And that means it's going to be a very powerful tool for predicting the future state of a system if we know its initial conditions, or vice versa. If we know the final conditions, we can predict what the initial conditions were. So that's what we're going to use it for, and I'm going to show you a few specific examples so you can actually see that in action. The first example we're going to look at is how we can use conservation of energy to predict the speed of falling objects. Okay, so essentially we're going to use the initial conditions to predict the final ones. This is how we're using conservation of energy. So in terms of the initial conditions, the object falls a distance of 5 meters on Earth. So that tells us our delta H is 5 meters. Strictly speaking, it actually means it's minus 5 because it's fallen a distance of 5. So it's asking how fast will it be traveling. So it wants to know what the final speed, or v, is. And it wants us to know that if we ignore the effects of drag or air resistance. And the reason it's important that it says that is that's what is telling us no work is done by external forces, which means the total energy is constant or stays the same. So that's the information we've given and kind of there. So let's now look at how we actually predict the final speed. Okay, so the starting point for this is going to be calculating how much GP the object loses. So we don't know the mass, so I'm just going to leave it as an m, and it's going to turn out later on we don't need to know the mass, so I'm just going to leave that as an m. We're on Earth, so g is 10, and then our height change is minus 5 because it's falling a distance of 5 meters. So the GP lost is 50 m. Okay, so therefore, we can conclude that the object gains 50 m of kinetic energy. Well, how do we do that? We're assuming that this GP that's been lost has been turned into kinetic energy because energy cannot be created or destroyed, it's just transferred. Okay, so how else can we calculate change in kinetic energy? Well, a change is always final minus initial. So change in kinetic energy is final kinetic energy minus the initial kinetic energy. So what we're going to do is we are going to assume it is initially stationary. So that's why this is a 0 in here. So it's initially stationary, and therefore it just becomes half mv squared is our change in kinetic energy. Now we've got two expressions for changing kinetic energy, we can get an expression for the final velocity in terms of the change in kinetic energy and the mass. We're just essentially rearranging this equation we've just got here. So then final step is we can actually plug some numbers in. So we're going to put 50m in for the change in kinetic energy, because that's what we've got here. And this is why we can see we didn't need the mass. Because you see the masses cancel out, so the speed the object is independent of mass. It doesn't matter on mass. And then we calculate it. That gives us a final speed of 10 meters per second once it's fallen 5 meters. Okay, so that's one example of it. Place where we can apply initial conditions to calculate final ones is finding an object's maximum height. So let's say we find an object upwards at 20 meters per second, calculate its maximum height. So essentially what this is telling us is that the initial speed, or u, is 20 meters per second, and it wants us to find the maximum height, or essentially we need to find out the height change of the object, because it said it's fired upwards from the ground. So the maximum height is going to be equal to the change in height. Okay, so we're going to assume that there's no drag or air resistance acting, so we can apply conservation of energy. So the first thing I'm going to do is figure out how much kinetic energy it's going to lose. Well, so that's essentially calculating the change in kinetic energy. Well, first of all, we're doing 0 minus half mu squared. Why are we doing that? Well, it's 0 here because it's stationary at maximum height, so it doesn't have any kinetic energy when it reaches the maximum height. So that's why there's a 0 in there. And the other thing to remember is change in something is final minus initial. So this is final kinetic energy, nothing, minus initial kinetic energy, half m, in this case, u squared, because we've got initial speed squared. So we can see that the change in kinetic energy is going to be minus 200m. So again, we don't know the mass, but again, it's not going to be important. Okay, so minus 200m. This is being transferred into GP. How do we know that? Because we're applying conservation of energy. So it's lost 200m of kinetic energy, so it's gained 200m of GP. We also know change in GP is mg delta h. So we can rearrange that to make delta h the subject. And then once we've done that, we can plug our value in for change in GP, 200m. We can cancel out the m, so max height is independent of mass as well. And therefore we can see that the change in height is just going to be 20 meters in this instance. Okay, so that's just two examples of applying conservation of energy. So I want to show you indicators that we should be applying conservation of energy in a question. First thing is, we can always be applying conservation of energy because it's a universal law. So if you're looking at something and you're not sure how to approach it, conservation of energy is a good starting point because it always works. Some indicators that I will use to notice a conservation of energy question is if we haven't been given a time, because all other methods to calculate distances and speeds all will require time. You know, for things like using acceleration, average speed equations, all those things, they all need time. And if we haven't got time, that's telling me conservation of energy is probably what we're using here. The other thing that I see is if in a question you're being given lots of height changes, because that's going to be indicating to you you should be thinking about GP. So again, something to look out for. Have you been given some height changes? You're probably using conservation of energy. Okay.